Hi everyone, I am Sham Parik. I am a student of BSc Chemistry Honours second year. My roll number is 10 and today we are going to read the chapter the D and the F block elements. The D block of the periodic table contains the element of the group 13 to 12 in which the D orbital are progressively filled in each of the 4 long periods. The F block consists of element in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The name transition metals and in transition metal are often used. There are many 4 series of the transition metal: 3D series scandium to zinc, 4D series yttrium to cadmium, 5D series lanthanum to hafnium 2, and 6D series which has elements from the 2 series of the inner transition metals 4f and 5f are known as lanthanides and actinides. Originally, the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation state and hence are not regarded as transition metals. However, being the end members of the 3D, 4D and 5D transition series respectively, their chemistry studies along with the chemistry of the transition metals. The presence of partly filled d or f orbital in their atoms make transition elements different from that of the non-transition elements. Hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum and industrially important metals like iron, copper and titanium belong to the transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence and general characteristics of transition elements with special emphasis on the trend in the properties of the first row transition metals along with the preparation and properties of some important compounds. This will be followed by consideration of certain general aspects such as electronic configuration, oxidation state and chemical reactivity of the inner transition metals. The transition elements. Point number 1, 4.1, position in the periodic table. The D block occupies the large middle section of the periodic table, flanked between S and P blocks in the periodic table. The D orbitals of the penultimate energy level of atoms receive electrons, giving rise to 4 rows of the transition metal, that is 3D, 4D, 5D and 6D. All these series of transition elements are shown in table 4.1. And now 4.2, electronic configuration of the D block elements. In general, the electronic configuration of outer orbital of these elements is n-1d1 to 10 n-1 to 2, except for palladium where its electronic configuration is 4d 10 5s0. The n-1 stands for the inner d orbital which may have 1 to 10 electrons and the outermost ns orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbital. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configuration of chromium and copper in the 3D series. For example, consider the case of chromium which has 3d5 4s1 configuration instead of 4d4 4s2. The energy gap between the two sets 3d and 4s orbital is small enough to prevent electron entering the 3d orbital. Similarly, in case of copper, the configuration is 3d10 4s1 and not 3d9 4s2. The ground state electronic configuration of the outer orbital transition elements are given in the table 4.1. Electronic configuration of outer orbital of the transition elements, ground state. Scandium, titanium, vanadium, chromium, manganese, iron, copper, nickel, cobalt, zinc. And Z is the atomic number which is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 respectively, and therefore S electronic configuration is 2, 2, 2, 1, 2, 2, 2, 2, 1, 2, and their 3D electronic configuration is 1, 2, 3, 5, 5, 6, 7, 8, 10 and 10. So here the chromium and copper which was supposed to be 1, 2, 3, 4 and then 7, 8, 9, but due to the small gap, it is 1, 2, 3, 5 and 6, 7, 8, 10 and 10. And for 2D series, it is yttrium, zirconium, nobelium, titanium, rubidium, rhodium, silver and cadmium. And yeah, so these are the series of these are the configurations. The electronic configuration of outer orbital of zinc, cadmium, mercury represent are represented by the general formula n-1d10ns2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. These are the elements of our 4D series, which starts with deuterium with atomic number 39, symbol Y, and electronic configuration. We will just discuss the outermost electronic configuration, which is 4d1 5s2. Then comes zirconium, having electronic configuration 4d2 5s2. Then niobium 4d4 5s1, molybdenum 4d5 5s1, technetium 45 5s2, ruthenium 47 5s1, rhodium 48 5s1, palladium 4d10 5s0, silver 4d10 5s1, cadmium 4d10 5s2. Now for the 5D series we have lanthanum 5d1 6s2, hafnium 4f14 5d2 6s2, tantalum 4f14 5d3 6s2, tungsten 4f14 5d4 6s2, rhenium 4f14 5d5 6s2, osmium 4f14 5d6 6s2, iridium 4f14 5d7 6s2, platinum 4f14 5d9 6s1, gold 4f14 5d10 6s1, mercury 4f14 5d10 6s2. And for the 6D series we have actinium 61 7s2, rutherfordium 5f14 6d2 7s2, dubnium 5f14 63 7s2, seborgium 5f14 64 7s2, bohrium 5f14 65 7s2, hassium 5f14 66 7s2, metadium 5f14 67 7s2, darmstadium 5f14 68 7s2, rontagium 6010 5f14 6010 7s1, and copernicium 5f14 6010 7s2. This was the electronic configuration of all the elements from 3D series, 4D series, 5D series and 6D series respectively. The electronic configuration of outer orbital of zinc, cadmium, mercury and are represented by the general formula n-1d 10ns2. The orbitals in these elements are completely filled in the ground and they are not regarded as transition elements. The d orbital of transition elements protrude to the property of an atom more than the other orbitals, that is S and P. Hence, they are more influenced by the surrounding as well as affects the atoms or molecules surrounding them. In some respects, ions of given dn configuration n equal to 1 to 9 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristics properties such as display of variety of oxidation state, formation of colored ions, and entering into complex formation with a variety of ligands. The transition elements and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail. There are greater similarities in the properties of transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and the trends in the horizontal rows and then consider some groups. So first of all, we will discuss about the physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exceptions of zinc, cadmium, mercury, and manganese, they have one or more typical metallic structure at normal temperatures. Like we will discuss about the lattice structure of transition elements. Scandium, it has HCP. Titanium, it has HCP. Body centered, and vanadium, it has BCC. Chromium, it has BCC, and manganese, it has BCC and CCP. Iron, it has BCC HCP. Copper, it has CCP. Nickel, it has CCP. Copper has CCPs, and zinc has HCP. The transition metals, with the exception of zinc, cadmium and mercury, are very hard and low volatility. Their melting and boiling points are high. Figure 4.1, this figure depicts the melting point of transition elements belonging to 3D, 4D and 5D series respectively. The high melting point of these elements are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electron to the interatomic metallic bonding. In any row, the melting point of these metals rise to maximum at 5d5 except for anomalous value of manganese and manganese and fall regularly as the atomic number increases. They have high enthalpies of atomization, which are shown in figure 4.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization, that is very high boiling point, tend to be noble in their reactions. Another generalization that may be drawn for figure 4.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in according for the occurrence of much more frequent metal-metal bonding in compounds of the heavy transition metals. In general, ions of the same charge in a given series show progressive decreased in radius with increased atomic number. So now we are discussing variation in atomic and ionic sizes of transition metals. This is because the new electron enter a d orbital each time to the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective. Hence the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series. However, the variation within a series is quite small. An interesting point emerges when atomic size of one series are compared with those of the corresponding element in the other series. The curves in figure 4.3 show an increase from the first 3D to the second 4D series of the element, but the radii of the third 5D series are virtually the same as those of the corresponding numbers of the second series. This phenomenon is associated with the intervention of the 4f orbital, which must be filled before the 5D series of elements begin. The filling of 4f before 5d orbital results in a regular decrease in atomic radii called lengthened contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lengthened contraction is that the second and the third D series exhibit similar radii. Example: zirconium 160 picometer, hafnium 159 picometer, and have very similar physical and chemical properties, much more than expected on the basis of usual family relationship. The factor responsible for the lengthened contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of one d electron by another, and as the nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4f orbitals. The decrease in metallic radius coupled with increase in atomic mass result in a general increase in the density of these elements. Thus for titanium, which has atomic number 22, to copper, which has atomic number 29, the significant increase in the density may be noted. Electronic configuration and some other properties of the first series of transition elements. So we are discussing about the first transition series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So they have their electron atomic number in the sequence 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And now let us discuss their electronic configuration. We will discuss only the outermost electronic configuration: 3d1 4s2, 3d2 4s2, 3d3 4s2, 3d5 4s1, 3d5 4s2, 3d6 4s2, 3d7 4s2, 3d8 4s2, 3d10 4s1, 3d10 4s2. And for like we are representing the elements as m. So for m positive, like when we remove one electron, the electronic configuration will be 3d1 4s1, 3d2 4s1, 3d3 4s1, 3d5, 3d5 4s1, 3d6 4s1, 3d7 4s1, 3d8 4s1, 3d10, and 3d10 4s1. And for m2 positive, it will be 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. And for m3 positive, for scandium, it will be only the noble gas, and after that it will be 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, and for copper and zinc it is blank. Enthalpy of, because they do not show 3 positive, because they cannot lose 3 electrons. Enthalpy of atomization, which is measured in kilojoule per mole inverse. It is 326, 473, 515, 397, 281, 416, 425, 430, 339, 126 respectively. So now let us discuss The ionization enthalpies. There is an increase in ionization enthalpy along each series of the transition elements. There is an increase in ionization enthalpy along each series of the transition elements from left to right due to an increase in nuclear charge which accompanies the filling of the inner d orbitals. Table 4.2 gives the value of the first three ionization enthalpies of the first series of transition elements. This value shows that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of the increase in the second and third ionization enthalpy for the successive element is much higher along a series. The irregular trend in the first ionization enthalpy of the metal of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energy of 4s and 3d orbitals. You have learned that when d block elements form ions, ns electrons are lost before n-1d electrons. As we move along the period in 3d series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3d orbital. These 3d electrons shield the 4s electron from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decreases less rapidly, thus ionization energy increases only slightly along the 3D series. The doubly or more slightly charged ions have dn configuration with no 4s electron. A general trend of increasing value of second ionization enthalpy is expected as the effective nuclear charge increases, because one d electron does not shield another electron from the influence of nuclear charge because d orbitals differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks for the formation of Mn2 positive and Fe3 positive respectively. The interpretation of variation ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the electrons, and the exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn positive has D3D5 4s1 configuration, and configuration of Cr positive is D5. Therefore, ionization enthalpy of Mn positive is lower than Cr positive. In the same way, Fe2 positive has D6 configuration and Mn2 positive has 3D5 configuration. Hence, ionization enthalpy of Fe2 positive is lower than Mn2 positive. In other words, we can say that third ionization enthalpy of iron is lower than that of manganese. The lowest common oxidation state of this metal is +2. To form the M2 positive ion from the gaseous atom, the sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper, where M positive ions have the D5 and D10 configuration. The value for Zn is correspondingly low, as ionization causes the removal of one 4s electron, which results in the formation of stable D10 configuration. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. Now we discuss about the oxidation states. One of the notable features of the transition element is the great variety of oxidation state they may show in their compounds. Table 4.3 lists the common oxidation state of the first row transition elements. Scandium +3, titanium +2 +3 +4, vanadium +2 +3 +4 +5, chromium +2 3 4 5 6, manganese +2 3 4 5 6 7, iron +2 3 4 6, cobalt +2 3 4, nickel +2 3 4, copper +1 2, and zinc +2. The elements which give the greatest number of oxidation state occur in the middle or near the middle of the series. Manganese, for example, exhibits all the oxidation state from +2 to +7. The lesser number of oxidation state at the extreme ends stems from either too few electrons to lose or share, or too many d electrons for higher valency. Thus, early in the series, scandium is virtually unknown and titanium is more stable than titanium 3 or titanium 2. At the other hand, the oxidation state of zinc is +2, no d electrons are involved. The maximum oxidation state of reasonable stability corresponds in value to the sum of the s and d electron up to manganese. followed by a rather abrupt decrease in stability of higher oxidation state, so that the typical species to follow are Fe2,3, copper 2,3, nickel 2, cobalt 2,3, nickel 2, copper 1 and 2, then zinc 2. The variability of oxidation states as characteristics of transition elements arises out of incomplete filling of d orbital in such a way that their oxidation state differ from each other by unity. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation state of the D block element is noticing among the groups. Although in the P block, the lower oxidation state are favored by the heavier members, the opposite is true in the group of D block. For example, in group 6, molybdenum and tungsten are found to be more stable than chromium. Thus, chromium in the form of dichromate in acidic medium is a stronger oxidizing agent, whereas MoO3 and WO3 are not. Low oxidation states are found when a complex compound has ligands capable of pi scepter character in addition to the pi bonding. Now we will discuss about trends in the M2 positive or M standard, that is standard electrode potential. Table 4.4 contains the thermochemical parameters related to the transformation of solid metal atoms to M2 positive ion in solution and their standard electrode potential. The observed value of E0 and those calculated using the data of table 4.4 are compared in figure 4.4. The unique behavior of copper having a positive E0 value accounts for its inability to liberate H2 from acids. Only oxidizing acids, nitric and hot concentrated sulfuric react with copper, the acids being reduced. The high energy to transform copper to Cu2 positive is not balanced by its hydration enthalpy. The general trend towards less negative E0 value across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of E0 for manganese, nickel and zinc are more negative than expected from the trend. Now the table 4.4 gives us the thermochemical data in kilojoule mole inverse for the first row transition elements and the standard electrode potential for the reduction of M2 to M. So the elements are titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. And their standard electrode potential values from M2 to M1 are 469, 515, 398, 279, 418, 427, 431, 339, 130 respectively. And their H1 values are 656, 650, 653, 717, 762, 758, 736, 745, 906 and so on. The stability of the half filled D subshell in Mn2 positive and the completely filled D10 configuration in Zn2 positive are related to their E0 values, whereas E0 for Ni is related, Ni is nickel, is related to the highest negative delta hybridization. An examination of the E0 M3 positive to M2 positive values shows the varying trends. The low value for scandium reflects the stability of scandium 3 positive, which has a noble gas configuration. The highest value for zinc is due to the removal of an electron from the stable D10 configuration of Zn2 positive. The comparatively high value for Mn shows that Mn2 positive with electronic configuration D5 is particularly stable, whereas comparatively low value for iron Fe shows the extra stability of Fe3 positive D5. The comparatively low value for vanadium is related to the stability of V2 positive half-filled T2G level. Table 4.5 shows the stable halides of the 3D series of transition metals. The highest oxidation number are achieved in titanium X4, where X is halogen atoms, tetrahalides VF5 and CrF6. The +7 state for manganese is not represented in simple halides, but MnO3F is known, and beyond Mn no metal has a trihalide except FeX3 and COF3. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in case of COF3, or higher bond enthalpy terms for the higher covalent compound, example VF5 and CrF6. Although V positive is represented only by VF5, the other halides however undergo hydrolysis to give oxo halides VUX5. Another feature of fluoride is their instability in the low oxidation state, example VX2, where X is Cl, Br or iodine. Now formula of halides of 3D metals. Oxidation state +6, it is chromium F6, +5 it is VF5 CrF5, and for +4, there are variety like TiX4, VX14, CrX4, MnF4. It is to be noted that X here represents two halogen atoms, and for +3 it is TiX3, VX3, CrX3, MnF3, FVX3, CuF3, and for +2 it is TiX2, VX2, CrX2, MnX2, FEX2, CuX2, and NiX2, and CuX2, and ZnX2. And for +1 oxidation state it is CuX3, and the same applies to CuX. On the other hand, all Cu2 halides are known except the iodide. In this case, Cu2 positive oxidizes I minus to I2. 2 Cu2 positive plus 4 I minus gives us Cu2 I2 in solid state plus I2. However, many copper 1 compounds are unstable in aqueous solution and undergo disproportionation. 2 Cu2 positive gives us Cu2 positive plus Cu. The stability of Cu2 positive aqueous rather than Cu positive in aqueous is due to the much more negative enthalpy of hybridization of Cu2 positive aqueous than Cu positive, which more than compensates for the second ionization enthalpy of Cu. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation state number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron Fe above Fe2O3 are known, although ferrites FeO4 (2 minus) are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, oxocations stabilize V5 as VO2 positive or V4 as VO2 positive and titanium 4 as TiO2 positive. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explain its superiority in the covalent oxide Mn2O7. Each Mn is tetrahedrally surrounded by oxygens, including a MnO-Mn bridge. Transition metals vary widely in their chemical reactivity. Now we will discuss about the chemical reactivity and E0 values. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 mH positive, though the actual rate at which these metals react with oxidizing agents like hydrogen ion is sometimes slow. For example, titanium and vanadium in practice are passive to dilute non-oxidizing acids at room temperature. The E0 values for M2 positive to M indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative E0 values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the E0 values for manganese, nickel and zinc are more negative than expected from the general trend, whereas the stabilities of half-filled D subshell D5 in Mn2 positive and completely filled D subshell in zinc are related to their E0 values. For nickel, E0 values related to the highest negative enthalpy of hydration. An examination of the E0 values for the redox couple M3 positive to M2 positive shows that Mn3 positive and CO3 positive ions are the strongest oxidizing agents in aqueous solutions. Now we will discuss about the magnetic properties. When a magnetic field is applied to substance, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Diamagnetism, substances are repelled by the applied field, which the paramagnetic substance are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons. Each such electron having a magnetic moment associates with its spin angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For this, the magnetic moment is determined by the number of unpaired electron and is calculated by using spin-only formula, that is mu under root n equals to under root n brackets n plus 2, where n is the number of unpaired electron and mu is the magnetic moment in units of Bohr magneton (bm). A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons. The magnetic moment increases with the increased number of unpaired electron. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electron present in the atom, molecule or ion. The magnetic moment calculated from the spin-only formula and those derived experimentally for some ions of the first transition element is given in table 4.7. The experimental data are mainly for hydrated ions in solution or in the solid state. Ion Sc 3 positive configuration 3d0 unpaired electron 0, and so their magnetic moment calculated is 0 as well as observed is also 0. Titanium 3 positive configuration 3d1 unpaired electrons 1, magnetic moment calculated is 1.73 and observed is 1.75. Titanium 2 positive 3d2 unpaired electrons 2, magnetic moment calculated is 2.84 and observed is 2.76. Vanadium 2 positive configuration 3d3 unpaired electrons 3, magnetic moment is 3.87 and observed is 3.86, and so on. For zinc 2 positive we have configuration 3d10 and unpaired electrons are 0, so its magnetic moment will also be 0. So here we can notice that in the table scandium 3 positive and zinc 2 positive have unpaired electron as 0 and thus their magnetic moment is also 0. More is the number of unpaired electron, more will be the magnetic moment. We shall discuss about the formation of colored. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solutions where water molecules are the ligands, the color of the ions observed are listed in table 4.8. A few colored solution of D block elements are illustrated in figure 4.5. Colors of some of the first row transition metal ions in aqueous solution from left to right: vanadium 4 positive, vanadium 3 positive, manganese 2 positive, iron 3 positive, cobalt 2 positive, nickel 2 positive, and copper 2 positive. And so in this figure these are the colors which the transition metal ions in their aqueous solution show. So now we will discuss about colors of some of the first row aquatic transition metal ions. Configuration 3d0, example scandium 3 positive, which is colorless. 3d0, example titanium 4 positive, colorless. 3d1, titanium 3 positive, purple. 3d1, vanadium 4 positive, blue. 3d2, vanadium 3 positive, green. 3d3, vanadium 2 positive, violet, and so on. And for zinc 2 positive, which has electronic configuration 3d10, it is colorless. So if we do not have any unpaired electrons, the metal ion in its aquated form will be colorless. Now we shall discuss about the formation of complex compounds. Complex compounds are those in which the metal ion bind a number of anion or neutral molecules, giving complex species with characteristic properties. A few examples are FeCN6 whole 3 minus FeCN6 whole 4 minus CuNH3 4 whole 2 plus 2 positive and PtCl4 whole 2 minus. The chemistry of complex compound is dealt with in detail in unit 5. The transition metal form a large number of complex compounds. This is due to the comparatively smaller size of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. Now we shall discuss about the catalytic properties. The transition metals and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium V oxide in contact process, finely divided iron in Haber's process, and nickel in catalytic hydrogenation are some of the examples. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. First row transition metal utilize 3d and 4s electron for bonding. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecules. The activation energy is lowering. Also, because the transition metals ions can change their oxidation states, they become more effective as catalysts. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. 2I minus plus S2OA2 minus gives us I2 plus 2SO4 2 minus. Now we shall discuss about formation of interstitial compound. Interstitial compounds are those which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattices of metals. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, titanium chloride and Mn4n Fe3H VH 0.56 and titanium H 1.7, etc. The formulas quoted do not, of course, correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of this compound are: they have high melting point, higher than those of pure metal. They are very hard. Some borids approach diamond in hardness. They retain metallic conductivity. They are chemically inert. Now we shall discuss about alloy formation. An alloy is a blend of metal prepared by mixing the components. Alloy may be homogeneous solid solution in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii that are within about 15% of each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum and manganese are used for the production of a variety of steels and stainless steels. Alloy of transition metals with non-transition metals such as brass and bronze are also of considerable industrial importance. Now we shall discuss about some important compounds of transition elements: oxides and oxoions of metals. These oxides are generally found by the reaction of metals with oxygen at high temperature. All the metals except scandium form MO oxide, which are ionic metal oxides which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxides, the oxocation stabilizes V5 as VO2, V4 as VO2 positive, and Ti4 as TiO2 positive. As the oxidation number of a metal increases, ionic character decreases. In the case of Mn2O7 is a covalent green oil. Even CrO3 and V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Thus, Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is, however, amphoteric, though mainly acidic, and it gives VO4 3- as well as VO2 positive salts. In vanadium, there is gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. V2O4 dissolves in acids to give VO2 positive salts. Similarly, V2O5 reacts with alkalis as well as acids to give VO4 3- and VO4 whole positive respectively. The well characterized CrO is basic, but Cr2O3 is amphoteric. Potassium dichromate K2Cr2O7. Potassium dichromate is a very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromate ore with sodium or potassium carbonate in free excess of air. The reaction with sodium carbonate occurs as follows: 4FeCr2O4 plus 8Na2CO3 plus 7O2 gives us 8Na2CrO4 plus 2Fe2O3 plus 8CO2. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate Na2Cr2O7.2H2 can be crystallized. Sodium dichromate is more soluble than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with potassium chloride. Na2Cr2O7 plus 2 KCl gives us K2Cr2O7 plus 2 NaCl. Orange crystals of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium in chromate and dichromate is the same. 2CrO4 2- plus 2H positive gives us Cr2O7 2- plus H2O, and Cr2O7 2- plus 2OH- gives us 2CrO4 2- plus H2O. The structures of chromate ion Cr042- and the dichromate ion Cr2O7 2- are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedrals sharing one corner with CrO-Cr bond angle of 126 degree. Sodium and potassium dichromates are stronger oxidizing agents. The sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. In acidic solution, the oxidizing action can be represented as follows: Cr2O7 2- plus 14H positive plus 6 electron gives us 2Cr3 positive plus 7H2O. It has E naught value of 1.33 volt. Thus, acidified potassium dichromate will oxidize iodide iod, will oxidize iodides to iodine sulfides to sulfur, tin 2 to tin 4, and iron 2 salt to iron 3. The half reaction are noted below. 6I minus gives us 3I2 plus 6 electron, 3SN2 positive gives us 3SN4 positive plus 6 electron, 3H2S gives us 3H positive plus 3S plus 6 electron, 6Fe2 positive gives us 6Fe3 positive plus 6 electron. The full ionic equation may be obtained by adding the half reaction for potassium dichromate to the half reaction for the reducing agent. Potassium permanganate, KMnO4. Potassium permanganate KMnO4 is prepared by fusion of MnO2 with an alkali metal hydroxide and an oxidizing agent like KNO3. This produces the dark green K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. 2 MnO2 plus 4 KOH plus O2 gives us 2 K2MnO4 plus 2 H2O, and then 3 MnO4 2 minus plus 4 H positive gives us 2 MnO4 negative plus MnO2 plus 2 H2O. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate. In the laboratory, a manganese 2 iron salt is oxidized by peroxydisulfate to permanganate. 2Mn2 positive plus 5H2OA2 minus plus 8H2O gives us 2 MnO4 minus plus 10SO42 minus plus 16H positive. Potassium permanganate forms dark purple, almost black crystals which are isostructural with those of KClO4. The salt is not very soluble in water, 6.4 gram out of 100 gram of water at 293 Kelvin, but when heated it decomposes at 513 Kelvin. It has two physical properties of considerable interest: its intense color and its diamagnetism, along with temperature-dependent weak paramagnetism. This can be explained by the use of molecular orbital theory, which is beyond the present scope. The manganate and permanganate ions are tetrahedral. The pi bonding takes place by overlapping of pi orbitals of oxygen with d orbital of manganese. The green manganate is permagnetic because of one unpaired electron, but the permanganate is dimagnetic due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalates to carbon dioxide, iron 2 to iron 3, nitrites to nitrates, and iodides to free iodine. The half reaction of reductants are 5COO minus and COO minus gives us 10 CO2 plus 10 electron, 5 Fe2 positive gives us 5 Fe3 positive, 5 NO2 minus gives plus 5 H2 gives us 5 NO3 minus plus 10 hydrogen plus 10 electron, 10 I minus gives us 5 I2. The full reaction can be written by adding the half reaction for KMnO4 to the half reaction of the reducing agent, balancing wherever necessary. If we represent the reduction of permanganate to manganate, manganese dioxide and manganese salt by half reaction, we get MnO4 minus plus electron gives us MnO4 minus, MnO4 minus plus 4 H positive plus 3 electron gives us MnO2 plus 2 H2, MnO4 minus plus 8 H positive plus 5 electrons gives us Mn2 positive plus 4 H2O. We can very well see that the hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetic of the reaction is also an important factor. Permanganate at H positive equals to 1 should oxidize water, but in practice the reaction is extremely slow unless either manganese ion are present or the temperature is raised. A few temperature oxidizing reaction of KMnO4 are: in acidic solution, iodine is liberated from potassium iodide as 2Mn positive plus 8 H2O plus 5 O2, and Fe2 positive ion green is converted to Fe3 positive yellow. Oxalate ion or oxalic acid is oxidized at 333 Kelvin. Hydrogen sulfide is oxidized. Sulfurous acid or sulfate is oxidized to a sulfate or sulfuric acid. In neutral or faintly alkaline solution, a notable reaction is the oxidation of iodide to iodate. Thiosulfate is oxidized almost quantitatively to sulfate. Manganese salt is oxidized to MnO2. The presence of zinc sulfate or zinc oxide catalyzed the oxidation. Now we shall discuss about the inner transition elements or the F block elements. The F block consists of the two series lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of the lanthanoids, for which the general symbol Ln is often used. Similarly, discussion of the actinoids include actinum besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do the members of ordinary transition elements in any series. They have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinoids is, on the other side, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements and partly because their radioactivity creates special problems in their study. The two series will be considered separately here. Now first of all we will discuss about the lanthanoids. The names, symbols, electronic configuration of atomic and some ionic states of atomic and ionic radii of lanthanum and lanthanoids, for which the general symbol Ln is used, are given in table 4.9. Now we shall discuss about the electronic configuration. It may be noted that atoms of these elements have electronic configuration with 6s2 common but with variable occupancy of 4f level. However, the electronic configuration of all the tripositive ions, the most stable oxidation state of all the lanthanoids, are of the form 4f raised to the power n. N equals to 1 to 14 with increases atomic number, atomic and ionic sizes. The overall decrease in atomic and ionic radii from lanthanum to lutetium, the lanthanoid contraction, is a unique feature in the chemistry of the lanthanoids. It has far-reaching consequences in the chemistry of the third transition series of the elements. The decrease in atomic radii derived from the structures of metals is not quite regular, as it is regular in M3 positive ions. This contraction is of course similar to that observed in an ordinary transition series and is attributed to the same cause, the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4f electron by another is less than 1d electron by another with the increase in nuclear charge along the series. There is fairly regular decrease in the size with increasing atomic number. The cumulative effect of the contraction of the lanthanoid series, known as lanthanoid contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. The almost identical radii of zirconium 160 picometer and hafnium 159 picometer, a consequence of the lanthanoid contraction, account for their occurrence together in nature and for the difficulty faced in their separation. Now we will discuss about the oxidation states. In the lanthanoids, La2 and La2 and Ln3 compounds are predominant species. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. The irregularity as in ionization enthalpies arises mainly from the extra stability of empty half-filled or filled F subshell. Thus, the formation of Ce4 is favorable by its noble gas configuration, but it is strong oxidant reverting to which the common +3 state. The E0 value of for Ce4 positive and Ce3 positive is plus 1.74 volt, which suggests that it can oxidize water. However, the reaction rate is very slow and hence Ce4 is a good analytical reagent. Pr, Nd, Tb and Dy also exhibit +4 state but only in oxides. MO2 EU2 positive is found by losing the 2s electrons in its F7 configuration account for the formation of this ion. However, EU2 positive is a strong reducing agent, changing to the common +3 state. Similarly, YB2 positive, which has F14 configuration, is a reductant. Now we shall discuss about the general characteristics. All the lanthanoids are silvery white soft metals and tarnish rapidly in air. The hardness increases with increasing atomic number, samarium being steel hard. Their melting point range between 1000 to 1200 Kelvin, but samarium melts at 1623 Kelvin. They have typical metallic structure and are good conductors of heat and electricity. Density and other properties change smoothly except for EU and YB and occasionally for SM and TM. Many trivalent lanthanoid ions are colored both in the solid state and in aqueous solution. Color of these ions may be attributed to the presence of F electrons. Neither La3 positive nor Lu2 positive 3 positive ions show any color, but the rest do so. However, absorption bands are narrow, probably because of the excitation within F level. The lanthanoid ions other than the F0 type, La3 positive and Ce4 positive, and the F14 type, YB2 positive and Lu3 positive are all paramagnetic. The first ionization enthalpies of the lanthanoid are around 600 kJ mole inverse. The second is about 1200 kJ mole inverse, comparable with those of calcium. A detailed discussion of the variation of the third ionization enthalpies indicates that the exchange enthalpy consideration appeared to impart a certain degree of stability to empty, half-filled and completely filled orbital F level. This is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium and lutetium. In their chemical behavior, the earlier member of the series are quite reactive, similar to calcium, but with increasing atomic number. Values for E naught for the half reaction are in the range of -2.2 to -2.4 volt, except for EU, for which the value is -2.0 volt, which is of course a small variation. The metals combine with hydrogen when gently heated in the gas. The carbides Ln3C, Ln2C3 and Lnc2 are formed when the metals are heated with carbon. They liberate hydrogen from dilute acids and burn in halogens to form halides. They form oxides M2O3 and hydroxides MOH whole thrice. The hydroxides are definite compounds, not just hydrated oxides. They are basic, just alkaline earth metals, oxides and hydroxides. The general reaction are depicted in figure 4.7. Lanthanoids is for the production of alloy steels for plates and pieces. A well-known alloy is mish metal, which consists of a lanthanoid metal 95% in iron, 5% in traces of sulfur, carbon, calcium and aluminium. A good deal of mismetal is used in Mg based alloy to produce bullets. Now we will discuss about the actinides. The actinides include the 14 elements from Th to Lr. The name, symbol and their properties of these elements are given in table 4.0. So the atomic number starts from 89 and ends at 103, and including the elements actinium, thorium which stands for Th, and Lr, which stands for lawrencium, actinium, thorium, potassium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. And the symbols are respectively Ac, Th, Pau, Np, Pu, Am, Cm, Bk, Cf, Es, Fm, Md, No, Lr. And their electronic configurations are 61 7s2, 62 7s2, 5f2. The f orbital starts from protactinium, 5f2, 61 7s2, 5f3, 61 7s2 and so on, 5f14, 61 7s2 for lawrencium. The actinides are radioactive elements and the earlier members have relatively long half-lives. The latest ones have half-life value ranging from a day to 3 minutes. For lawrencium, Z equals 103. The latest member could be prepared only in nanogram quantities. These facts render their study more difficult. Now we will discuss about their electronic configuration. All the actinides are believed to have the electronic configuration of 7s2 and variable occupancy of the 5f and 6d subshell. The 14 electrons are formally added to 5f, though not in thorium where atomic number is 90, but from Pa onwards. Pa, which stands for protactinium. The 5f orbital are complete at element 103, which is lawrencium. The irregularities in the electronic configuration of the actinoids, like those in the lanthanoids, are related to the stabilities of the F0, F7 and F14 occupancy of the 5f orbitals. Thus the configuration of Am and Cm. Am, which stands for americium, and Cm, which stands for curium, are Rn. Rn is a noble gas, 5f7 7s2 and Rn 5f7 61 7s2. Now we shall discuss about the ionic sizes. The general trend in lanthanoids is observable in the actinoids as well. There is a gradual decrease in the size of atoms or M3 positive ion across the series. This may be referred to as actinoid contraction, like lanthanoid contraction. Now we shall discuss about the oxidation state. There is a greater range of oxidation states which is in part attributed to the fact that 5f, 16, 7s level are of comparable energies. The non-oxidation states of actinoids are listed in table 4.11. The actinoids show in general +2 oxidation state. The elements in the first half of the series frequently exhibit higher oxidation state. For example, the maximum oxidation state increases from +4 in thorium to +5, +6 and +7 respectively in practimicium, uranium and neptunium, but decreases in succeeding elements. The actinoids resemble the lanthanoids in having more compound in +3 state than in the +4 state. Now we shall discuss about the general characteristics with comparison with lanthanoids. The actinoid metals are all silver in appearance but display a variety of structure. The structural variability is obtained due to irregularities in metallic radii which are far greater than in lanthanoids. The actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydride, and combination with most non-metals take place at moderate temperature. Hydrochloric acid attacks all metals but most are slightly affected by nitric acid, owing the formation of protective oxide layers. Alkalis have no action. The magnetic properties of the actinoids are more complex than those of the lanthanoids, although the variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electron is roughly parallel to the corresponding results for the lanthanoid. The latter have high value. It is evident from the behavior of the actinoids that the ionization enthalpy of the early actinoids, though not accurately known, but are lower than for the early lanthanoids. This is quite reasonable, since it is to be expected that when 5f orbital are beginning to be occupied, they will penetrate less into the inner core of electrons. The 5f electrons will therefore be more effectively shielded from the nuclear charge than the 4f electron of the corresponding lanthanoids. A comparison of the actinoids with the lanthanoid with respect to different characteristics, as discussed above, reveals that behavior similar to that of the lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoid in showing close similarities with each other and in gradual variation in properties which do not entail change in oxidation state. The lanthanoid and actinoid contraction have extended effect on the size and therefore the properties of the elements succeeding them in their respective periods. Now we shall discuss about some application of D and F block elements. Iron and steel are the most important construction materials. Their production is based on the reduction of iron oxide, the removal of impurities, and the addition of carbon and alloying metals such as chromium, manganese, and nickel. Some compounds are manufactured for special purpose such as TiO for the pigment industry and MnO2 for use in dry battery cells. The battery industry also requires zinc and nickel or cadmium. The elements of group 11 are still worthy of being called the coinage metals, although silver and gold are restricted to collection items, and the contemporary UK copper coins are copper coated steel. The silver UK coins are a copper or nickel alloy. Many of the metals and or their compounds are essential catalysts in the chemical industry. V2O5 catalysts the oxidation of SO2 in the manufacture of sulfuric acid. TaCl4 with AlCH3 whole thrice forms the basic of Ziegler catalyst used to manufacture polythene. Iron catalysts are used in the Haber process for the production of ammonia from N2 or H2 mixtures. Nickel catalysts enable the hydrogenation of fats to proceed in the Waker process. The oxidation of ethine to ethanol is catalyzed by PdCl2. Now we are heading towards the summary of this chapter. The D block consists of group 3 to 12, occupies the larger middle section of the periodic table. In this element, the inner d orbital are progressively filled. The F block is placed outside at the bottom of the periodic table. Corresponding to the filling of 3d, 4d and 5d orbital, three series of transition elements are well recognized. All the transition elements exhibit typical metallic properties such as high tensile strength, ductility, malleability, thermal and electrical conductivity, and metallic character. The melting and boiling point are high, which are attributed to the involvement of n-1d electrons, resulting into strong interatomic bonding. Successive ionization enthalpies do not increase as steeply as in the main group elements with increasing atomic number. Hence, the loss of a variable number of electrons from n-1d orbital is not energetically unfavorable. The involvement of n-1d electrons in the behavior of transition elements imparts certain distinct characteristics to these elements. The transition elements vary widely in their chemical behavior. Many of them are sufficiently electropositive to dissolve in mineral acid, although few are noble. Of the first series, the exception is with copper. All the metals are relatively reactive. The transition metals react with a number of non-metal like oxygen, nitrogen, sulfur and halogen to form binary compound. The first series transition metal oxides are generally found from the reaction of metals with oxygen at high temperature. These oxides dissolve in acids and bases to form oxometallic salt, potassium dichromate and potassium permanganate as common example. The two series of inner transition element lanthanoid and actinoids constitute the F block of the periodic table with the successive filling of inner orbitals 4f. There is a gradual decrease in the atomic ionic size which is known as lanthanoid contraction. This has far-reaching consequences in the chemistry of the elements succeeding them. Lanthanum and all the lanthanoids are rather soft white metals. They react easily with water to give solutions giving +3 ions. The principal oxidation state is +3, although +4 and +2 oxidation state are also exhibited by some occasionally. There are many useful applications of the D and F block elements and their compounds, notably among them being in variety of steel, catalyst, complexes, organic synthesis, etc. So this was all for about our D block elements from the NCERT book. Thank you all for watching. Subscribe my channel for more such videos.